All right, so remember that series circuits have but one current, yet many voltages, right? So let's draw this current here. It's going to go red, and then this way, and then this way, this way. All right, there we go. So that's just one current. There's no current does not go along the leads to voltmeters because remember these guys have an internal resistance of infinity. Current does go through the ammeters. That's how the ammeters know the current. You can measure it, right? Because it has to go through them. These guys have a resistance of 0. They don't affect the current, right? So current is not going along these wires because this is like an infinite resistor. Okay. Now in reality, it's millions of ohms. Okay. So the first thing I want to do here is I want to find the total resistance, right? This is what you always do, right? So it's 2.4 plus 1.3 plus 6.1 plus 3.4. All right, here we go. So 2.4 plus 1.3 plus 6.1 plus 3.4. And that's 13.2 ohms. That's total, right? Because resistors add in series. The next thing is to find the one current, right? So the one current is the source voltage, this guy here, right? Divided by 13.2. So 13 divided by the answer I just got is 0.984848. A lot of 4/8. And that repeats, okay? That is going to be the current read by this ammeter and this ammeter, right? So 0.98, I guess 985, right? So this current is V over R. It's 13 divided by 13.2, 0.985, same current. All right, so now let's find the voltages, right? Voltages you will find by going IR, okay? So V is IR. So what you do is you go from the upstream side to the downstream side. What total resistance did we find? 2.4, and that's it, right? So it's going to be the one current. So 0.9848, repeating, right? Times 2.4. Okay, I'm going to store that in A, and then I'm going to go times 2.4. And I get, 2.36, and the 3 6's repeat. This is awesome. I love numbers. All right, there you go. So 2.36, that's the answer there, right? And this one's going to be V is IR. So V2, and of course this is tricky, right? So we go here and then just follow this. How many resistors do we count? No, ammeters don't matter. Voltmeters don't matter. Just ignore them. How many do we find from here to here in the line of the current? 6.1 plus 3.4, right? So that is 0.9848, repeating, times 6.1 plus 3.4. All right, so alpha A times 6.1 plus 3.4. And that's 9.3560606006. Once they start repeating, they never stop. Okay, so that is 9.36. Okay, V3. Okay, so we start here and we end here. How many resistors do we encounter? None. Okay, so this is IR. So it's 0.9848 repeating times 0, and that is 0. Okay, it's not 0.9848. We're not adding those. Okay, now this is by the way is the only thing that caused people any problems in the past. So let's be careful about this, right? In a series circuit, because we know the current and we know the resistance, we are going to use the formula power is I squared R. Now we could find the voltage and use I times V or V squared over R, but this is the simplest way to do it. Now all of these resistors have the same current. They just are different resistances, right? So for example, this power of this resistor would be this current 0.985 squared times 2.4, and that would be 0.985 squared times 1.3 and 0.985 squared times 6.1, etc., etc. Okay? The greatest power, therefore, is going to be the largest resistor. Since everything is the same, right, then the largest resistor would give you the greatest power, and the smallest resistor would give you the smallest power. Okay? So let's just do that. Power is I squared R. So that's 0.9848 repeating squared times the biggest resistor to give the biggest power. I hope that makes sense. So I'm going to go alpha A, where I stored that, square that times 6.1, and I get 5.916, so 5.92 watts. Now, let's suppose that in the future the worst possible thing happens, and that is you forget all this, right? So let me just give you this clue. You can read this. This is in English, right? Greatest power dissipated by a resistor. The other thing you know for sure is that the smallest resistor is either going to be the greatest power or the least power, and the biggest resistor is going to be the greatest or the least, right? So if you forget, find the power due to each one. Right? This is the smallest, this is the biggest, right? Find the power dissipated by each one. One will be larger and one will be smaller, and the larger would be what you'd use here. Okay? None of the resistors that are in the middle are going to be the greatest or smallest, right? They'll be somewhere in between. Okay? So if you forget, just simply calculate the power of maybe every resistor, right? Okay, and then pick the greatest. All right, that's the one. What people would do is they would be like, well, it's the 1.3, because see, here's the thing. In a parallel circuit, it's exactly the opposite. The smallest resistor dissipates the greatest power. Here, the largest one does, right? So it's a little bit tricky, All right.